Hi 106 TAs, this is Chris True, and I put together this video to show you some of the things that you can do with GeoGebra to help you teach your 106 classes, and especially with the part about optimization. I've put together this Word document, and I haven't formatted this so I've given them any room, but you can fix that if you want to. So I've just given them kind of 5 typical kinds of problems with optimization, and I want to take each one of these and demonstrate how you could demonstrate these problems using GeoGebra and helping the students get to the point where the problem is that I think that the biggest problem with students is that they have a hard time kind of modeling the function, and then once they get the function modeled, then they just have to take the derivative, find the critical points, and so on. Once they get to that point, then I don't think it's as much of a challenge for them. So I want to take a look first of all at you can get GeoGebra. It's just at geogebra.com, and this, I think, because I'm on a Mac, I think it pulls this up for Mac specific, but if you just go over here to GeoGebra free download, it's a software package that's totally free. There's a lot of other online resources. If you just Google GeoGebra, there's a whole community out there, the listserv and things like that, with a lot of support. So if you can go and download that, and then once you've got it downloaded, then the files that I've given you access to, you'll have full access to editing and manipulating them in your class if you want to. Okay, so let's go back to that first problem. The first problem was about you got a line. Y equals 4 minus 1/2 x. We want to inscribe a rectangle underneath that, a very typical kind of a problem that students might see in a textbook. So to model that in GeoGebra, I've set up a file. It's just called question number 1, and if we open that one up, you get something that looks like this. Okay, and GeoGebra is a program that ends up being very dynamic. I've set this up ahead of time, but I've got a problem that I will walk you through how to set up one of these files just on your own. And the dynamic part about this one is that this point B is movable. And so the problem asks, of all the rectangles that you could form underneath this line, which one has the largest area? And so students could just kind of investigate as they pull this along. They could see that that function keeps getting bigger and bigger until they get to a certain point. And because of the rounding here, it looks like there's a couple places where it's equal to 8, but then it starts to drop off again. All right, so it looks to me like right about there is the biggest rectangle that we're going to get. All right, so what students are going to need to do then is come up with some kind of a model for a function that models the area of this rectangle. All right, now before we get to that point where we're going to, we'll call this side down here x, and we'll call this side 4 minus 1/2 x, I want to see about modeling this a little bit ahead of time with looking at just finding the area of this and plotting a function that, or just plotting a point and tracing it, that gives me the area of the rectangle. All right, so what I'm going to do is just go up here and select a point and just drop it down here in the plane. And I'm going to right click on that point. And what I'd like this point to give me is an x coordinate that is the same x coordinate as this point B. So I'm going to go up here and just edit the coordinates. And I'm just going to call this, the command is just x and then kind of in parentheses b. And then what I want the y coordinate to be is the area of that rectangle. And I've already set up a formula over here. It's E that is defining the area of that rectangle. So I'm just going to replace this with E. Okay, and then close it. All right, so we've got that point up here, corresponds to the x coordinate of this point, and the y coordinate is equal to 4.47 at this point, the area of that rectangle. So if I drag this along, you can see that that point is moving upward, which means the function is increasing, and then it reaches some kind of a peak, and then you'll see that it starts to fall off again. Okay, so I'd like to see that in the screen, so I'm going to just zoom out here a little bit, and we'll try that again. All right, so That point is just moving up and down, and it's going to be following some kind of a function that models the area of the rectangle. Now, a nice thing about this is I can double click or right click on this again, and I could say just turn the trace on. And what it'll do is trace that path or that locus of points, and then it comes down again. All right, so if I could just come up with a function that defines, it looks like this parabola, then all I'd have to do is maximize that function. Okay, so if we solve that problem the way we typically would, we're going to take that picture and we're going to say, okay, we're going to go out here a certain distance. We'll call this x, and then because this line has the equation y equals 4 minus 1/2 x, the height of this is going to be just 4 minus 1/2 x. Alright, so we're going to get an area function that is just a function of x that is x times 4 minus 1/2 x. Okay, and so that function is the function that I want to take advantage of. Alright, so if I go back to GeoGebra and I just type in that function, x times 4 minus 1/2 x, and graph it, we can see that that parabola over here is exactly the same as that locus of points. All right, so it gives the kids an opportunity to kind of get the idea of the modeling first and then come up with the actual function. All right, so from there, obviously we're just going to find the derivative of this. So 4x minus 1/2 x squared is again a of x. Take the derivative of that, you're going to get 4 minus x, and you're going to find out that that's equal to 0 when x is equal to 4. Okay? All right, and then if you go back to the function again, or to GeoGebra, you see that when x is equal to 4, this function does take on a maximum value. Okay? Something else that we could look at here is I'd like to be able to verify that there is actually a max there. I think it's obvious from what I've got drawn on here, but if we graph the derivative of this, the derivative is just 4 minus x, and graph it, this function right here is the derivative of that function, and you see that when x is equal to 4, you're going to get the derivative is equal to 0. Over on this side of 4, the derivative is above the x-axis, so it's positive. So the function's increasing and then the function's decreasing. They can use the first derivative test here with a graph of the derivative. So I think that's kind of cool too. All right, so let's take a look at another problem. The second problem is almost the same kind of problem, except this one ends up with you got a parabola instead of a linear function. All right, so if we go back to GeoGebra, I've got this one set up for you as well. We could have, I suppose, just taken this function and just changed this function here to the parabola, and we'd end up with the second problem. But let me open up question number 2. And question number 2 is very similar. This is going to be a dynamic point that I can move around. All right, so we could go through the same kind of drill on this problem. So if we want to get an idea what the answer is, it looks like the answer is going to be somewhere right around this range somewhere, a little bit, maybe like 1.75 or so. Okay, so kids can go through that problem and solve that one just the same way that they did the other one. Okay, all right, next problem. Question number 3. This one is a little bit more a more difficult type of a problem. It's a right triangle. We've got this graph of y equals e to the negative x. We're going to form a tangent line to this curve, and then it's going to form a triangle in the first quadrant. All right, so the file that I have made up for that one looks like this. Question number 3. Okay, and so here's the graph of e to the negative x. I've got a point on the graph. GeoGebra allows you to graph tangent lines to curves, and then this point is dynamic, and it's going to determine the area of this triangle. All right, so if I take that point and move it, we can see that that area is increasing, until we get to about here, and then it starts to decrease again. So it looks to me like the answer to this is going to be somewhere around 1. All right, and so once you've showed the students that, then I think you can probably just go through and find the function that models the area of this triangle. You're going to need the equation of the tangent line, and you're going to have to find the two legs and then find the area of the triangle. It's a lot more involved than the other two problems. But still, another one that you can represent what this looks like dynamically and then go back and solve it analytically. All right, so next problem then is this is a line segment has two endpoints on the x and y axis, and it's going to go through the point 3,8. We want to find out which one of the line segments is going to be the shortest one. All right, so again, this is already set up in GeoGebra for you. Question number 4. Okay, and so the dynamic part of this one is here, that as I move this, you see the length of that line segment changes, and there's going to be some point in here where we're going to end up with the shortest line segment. Okay, and so for this one, if I wanted to find the length of that and do kind of the same thing I did before with plotting a point and tracing the path, this is what would be involved. It's just come up here and grab a point, and we're going to change the coordinates of this point. We're going to make this just the x coordinate of the point B. And then we need a y coordinate. All right, now to find the y coordinate, I need to know what's the length of this line segment. You can see I've already got that set up as 15.33, but let me demonstrate how I did that. I just go up here to this thing, which is a measuring tool, and I'm just going to say I want to find distance. And the distance that I want to find is this line segment, the length of the segment BC. All right, so I just click on it, and it tells me that that line segment is 15.33 units. Okay, and you can see that it's been assigned the variable b. All right, so if I go up here to this point, I want the y coordinate to be whatever b happens to be. All right, so we'll get rid of that 14 point something, and we'll just put in lowercase b. Okay, and then close it, and now we've got this function up here, or this point, that is going to kind of go up and down, and then I'd like to be able to trace that and trace on, and we can see that that function is decreasing until I get to about this point, and then it starts to increase again. So it looks like there's going to be a minimum value on this function somewhere, what is that, somewhere around 8 or so. Okay, now, so the challenge is come up with a function that models this curve up here, and then find the derivative of it, set it equal to 0, and so on. Okay, this last one, I want to show you the problem, and then we'll open up a blank GeoGebra file, and I want to show you how you can create your own file to model what's going on in the problem. So the problem is this. This guy is 200 yards out on a straight shoreline. He catches a huge fish and wants to show his buddies at the marina. The marina is 600 yards down the shore. He can row at a rate of 3, and he can run at a rate of 5. And we want to know, where should he land his boat in order to get to the marina in the shortest amount of time. Alright, so if we go to GeoGebra, and I'm just going to say let's open up just a new file. And the first thing I want to do is scale the axes here. It said that he was 200 yards away from the shore, so let's say that the x-axis is the shore, and we'll put a point out here at 200. So in order for me to do that, I'm going to have to right-click on the axis, go down to Graphics, and the first thing I want to do is scale this. So the x, well, it said it was 600 yards down the shore, so let's go from like -100 to, we'll say 700 on the x-axis. And then on the vertical axis, let's go from like -100, and it said he was 200 yards away, so let's go out to like 300. Okay, and then the other thing is I see that the grid is kind of a mess now, so let's let's first go to the x-axis, and I just want the distance between those to be 100. And let's also do that on the vertical axis. We'll make these 100. Okay, so there's my scale. All right, now I wanted to plot a point out here 200 yards away from the shore, and so we'll go up here and we'll just grab a point. And I think before I do that, I wanted to lock right down on this point 0, 200. So under options, there's a point capturing, and I can tell it to snap it to the grid, which just means that when I get close to a point of intersection, it's going to snap to it. So we'll select a point, we'll put it here at 200, and you can see that it plotted that point A. All right, and then we've also got a point at the marina. The marina's over here at 600, 0. And there I've got that point locked in. Okay, then, so he's going to catch a fish out here. He's going to row to the shore someplace, and then he's going to run down the shoreline. All right, so we're going to need another point, and that other point is just going to be somewhere along this axis, or along the x-axis, yeah. All right, so now I just need to know a couple things. I want to know how far is it from here to here, so I can figure out what the time is. So I'm going to need to draw a line segment, and just say, give me the line segment that starts at A and ends at C. Okay, and then I need another line segment that starts at C and ends at B. Okay, and then some other things that I can do is I can grab this and just change the way this looks. Maybe I want this to be in red, and maybe I want that line to be a little thicker. All right, so I can do things like that. And then I can do the same thing with this one. We'll make that thicker, and let's make this one, I don't know, blue, and then close it. Okay, so now I have a picture that I have this point is free moving. All right, if you see that when you get close to the hundreds, it locks in on them. All right, I can change that again by just going up to the options and saying, you know, don't snap to the grid anymore, okay, because we're going to want to move this thing kind of smoothly. Okay, so now the idea is we're going to need the lengths of these two line segments. So I'm going to go up and grab my measuring tool, distance, and I just want to find the distance of this line segment. Okay, and it tells me that that distance is, what is it, 247 point something? And then I'm also going to want to know what this other distance is. Okay, and it happens to be right now 454. Okay, now the question on this one was not what is the shortest distance to the marina, because if it was, then we would just, you know, we would just go straight to the marina like that. Okay, but the problem is that he can't row as fast as he can run, so he probably wants to take advantage of his speed along the shoreline. So now we need to model a function that will give us the time that it's going to take him to get to the marina. All right, so the problem said that he can row at a rate of 3, he can run at a rate of 5. All right, so we need to come up with a function or some way to model that time. How long is it going to take him to get there if I leave the picture the way it is? All right, so we need to think a little bit. If think about the formula, distance is equal to rate times time, but what we're trying to minimize is the time, so we're going to end up with our function being time is equal to distance divided by rate. All right, so I want to take the distance here, which is right now at 210.42, and I want to divide it by how fast he can row, which is 3. So I'm going to just define another value down here in the input line. I'm just going to say take the distance from A to C, which is up here as just lowercase a, and we're just going to divide that by 3. And then we're going to add to that the distance that he's going to run, and we're going to divide that by how fast he can run, which is 5. So that's just going to be b divided by 5. Okay, and then when I hit enter, I get this value, c is equal to 177.06, and that's the time it's going to take him if he lands his boat here. All right, so again, what I'm interested in knowing is when is this thing going to be smallest? So if he rows directly to the shore and then runs down the shoreline, we can see that that C is 186.7, and as we move this way, we can see that that is getting smaller. All right, if we keep moving across here, it looks like it's still decreasing until we get somewhere in here, and then it looks like it starts to increase again. All right, so what we want to know then is where is that value in here where we end up minimizing the time. All right, so if we do that same trick with trying to just trace out the curve, we're going to just plot a point up here, and then I'm just going to right click on that point and get our properties, and we want basic properties, and again I just want to change the coordinates of this point. I want the coordinates of this point to reflect the x coordinate of C, so x of C, and then I want the y coordinate to be the time, and the time was lowercase c. All right, so we'll just change that 170 point something to lowercase c, and we'll close that window. All right, so we get this point up here, and then again, as I move this point, we can see that d changes. Okay, that function does not change very drastically, but it does, kind of drop down and go back up, and so we want to trace it. So I just turn the trace on and drag away. All right, so it looks like it's decreasing, and then we reach a point in here where it starts to increase again, and then it looks like if we go too far down here, and obviously I don't think we want to go past the marina, and I don't think we ever want to go back over this way. So we're just talking about something between 0 and 600 is going to be where we want to land our boat. And it looks like the answer is going to be, looks like about 150. Okay, so that's one thing we could do, and without actually coming up with the function yet. The next thing I want to look at is, what is this function? All right, so we're going to want to analyze this a little bit. So we'll go back to our whiteboard or our paper, and we're going to end up with a picture that looks something like this, where this is 200. This is, we'll call it x, and so the length of this hypotenuse is going to be the square root of 200 squared plus x squared. Okay, so that's the distance that he's going to row, and so our time function is going to be a function of x. It's going to be the distance rowing, square root of 200 squared plus x squared divided by 3, plus, then we want to know how far is it from here to 600. Okay, so that's just going to give me 600 minus x, and so we're going to take 600 minus x and just divide by 5. All right, so this is the function that I want to minimize. All right, so if I go back to GeoGebra then, and I put that function in and plot it, it should give us just this blue graph up here. So that was square root of 200 squared plus x squared. Close that. We're going to divide that by 3, and I'm going to just embed some parentheses in here just to make sure. All right, so that's the time rowing plus the time running is 600 minus x divided by 5. Oops, I got an error in there someplace. Okay, and for some reason it put 484 in there instead of 200 squared. Okay, so 200 squared. Okay, so there's the function. You can see that it's on top of that curve. So if I get rid of the trace and put it back on there, you can see that that point D traces right along that path. Okay, so now the idea is we want to find the derivative of this function, set it equal to 0, and if you look at the derivative of this, it's going to be a little bit of chain rule, and then we're going to have to find out where is it equal to 0, and it's going to be kind of a challenge to find the answer to that one. So what I would like to do is have GeoGebra do some of that work for me, and I can tell it just to find the derivative, and I want to find the derivative of this function, which it has defined as just f. Okay, and GeoGebra will do this and come up with this function. Okay, so I want to find out where this is equal to 0, which is going to be a bit of a challenge to solve algebraically, but I can also find out where this is equal to 0 if I just graph it. And I think that the graph is on there. It's just that it's the scale here is very large, and you can see that this function doesn't increase very quickly. So I want to go back to my axes, and I want to scale this down because I want to know where this thing crosses the x-axis. So we'll go back to axes, and whoops, not that. Let's turn the axis off. I want to go back to graphics, and I'm interested in the y-axis, and we need to put some limits on this. Okay, I'm going to say let's go from not negative 100, but let's maybe go from like negative 20 to positive 20. All right, so we're kind of zooming in along the x-axis a little bit more. All right, and maybe I need a little bit more than that. So let's go back to graphics, and let's make this not negative 20. How about negative 2 to 2? Okay, so then I can see this is the derivative of that function. And I'd like to know, where does this cross the x-axis? So I've got a way of doing that up here. There's find the intersection, put a point at the intersection of two things. So I want to know, where does this function intersect this axis? Okay, and it puts a point right there at E, and if we come up here we see that E is equal to 150 and 0. Alright, so it looks like the solution to setting this equal to 0 is going to happen when x is equal to 150. Alright, then I like to have students look at this and say, alright, is there a min or a max there? And we've already seen the graph, so we know the answer, but how about using the first derivative test? This is the derivative of the function. It's negative over here, and then it's 0, and then it's positive again. So what is the function doing? It is decreasing and then increasing, so there's a local minimum at this point, 150. Okay, and then this one also, I think if we did this on a closed interval, we could say, what's the value of the function at 0? What's the value of the function at 600? What's the value of the function at 150? We're still going to get the same answer, that we should land the boat right here. Okay, so I know that this section has been traditionally a section that students have struggled with, and I'm always looking for ways like this to help students understand the nature of the problem. You might encourage your students to download GeoGebra. Some of them might want to play with it a little bit. It's a nice way to do some investigations and just to do some what ifs. What if we change the parameters, how fast this guy can row and how fast he can run? What's that going to do to my answer? So there's a lot of things that you can do there just by quickly changing the functions. So I hope you find this useful, and if you've got any questions about it, or if you have any other ideas, or you want to share with some other people in the department, please let me know, and we'll get it out there to everybody to share. So if you decide that you are going to use this in class, I would really appreciate it if you would give me an email and let me know, and I'd love to come in and watch it. And if you want me there to kind of help run the show, I'd be more than willing to help you do that as well. So again, I hope you find this beneficial, and enjoy the rest of your weekend, and we'll see you sometime later on this week. All right, thanks.